Okay, so welcome back to another video. So here today we have a nice little infinite sum slash of an identity that we would like to find a nice closed form. And what we have is, of course, it's interesting that we have a Riemann-Zeta function and everything is dealing with in terms of like the even indices. When you expand this out, we have the infinite sum from n is equal to 1 to infinity of the Riemann-Zeta at 2n multiplied by x to the power 2n and divided by 2n. So I think what's great is interesting is that if you were to find the first initial steps on how to, go through this process is, of course, we want to utilize the definition of the Riemann-Zeta function. And this implying that what we're really dealing with in terms of the simplification so far is that we're actually working with a double sum. And it's also nice that afterwards, when we come down to that simplification, we actually are going to be utilizing two of Euler's interesting formulas. One is actually the infinite sine product and the reflection formula. So that's utilizing the gamma function. And it's, the recurrence relation formulas we'll be utilizing to, replace, substitute, and then simplify it all out. And also I forgot to mention that we have our x values. So this is actually, we're finding that converges such that the absolute value of x is strictly less than 1. So forgot to put that down, but that's actually our condition that we'll be utilizing as well that is given. So with that, I pretty much just said we'll give away the entire outline. So why don't we actually just jump right in? So let me first write down some definitions. So for one, of course, the Riemann-Zeta function, we know that. So it's equal to 1, our indices. So let me actually write this as a different notation. I'll write this as m. So m is equal to 1 of 1 divided by m to the power 2n, such that, of course, that's going to equal to the Riemann-Zeta 2n. So we'll actually be utilizing that substitution. So putting that back in, what I have is, so now the Riemann-Zeta, or our infinite sum first, n is equal to 1 of x to the power 2n and then divided by 2n, then multiply with the summation definition of the Riemann-Zeta. So multiply that. So m is equal to 1 of 1 divided by m to the power 2n. So if I put this back together as a double sum, so that's the product, and then there's actually a nice proof of verifying the identity. If you have a product of sums, you could put that together as a double sum, of course, combining with the indices together. So what we have now is that, and I'm also going to factor out 2 as well. So I have 1/2 and then multiply by our double sum. So the index I'm going to write first is m is equal to 1, and then n is equal to 1 of, now this is going to be x to the power 2n and then divided by n times n to the power 2n. So what I can do here is let's actually simplify this. So I'll actually factor out the exponent n. So I have 1/2, and then of course we still have our double sum notation over here. M is equal to 1, and then n is equal to 1. And then factoring out that exponent for n, so what we have is that I have x squared and then divided by m squared. So that's the quantity to the power n and then divided by n. And so what's great is that we can actually utilize a nice series expansion of the following function. So what we have is that specifically the natural log of 1 minus x is going to equal to the following series expansion. This is actually going to yield out to negative the infinite sum starting at our index at m is equal to 1 of x to the power m and then divided by m. And of course, this is for such that x, the absolute value of x is strictly less than 1 for our convergence. So of course, this is nice that actually verifies that condition, since no matter for m and then x that we have our what we're given, that it actually still converges either way. So with that, now I can actually rewrite this. So now I have a negative 1/2, and then now we have our infinite sum. So this is what for m is equal 1. And then rewrite this as the natural log of 1 subtract x squared divided by m squared. Okay, so now this leaves the question on how do we proceed forward with here. So we're actually going to specifically just pay attention to our infinite sum over here. Well, the natural log of 1 minus x squared divided by m squared. So with that in mind, this is where, of course, one of Euler's great formulas comes in handy, specifically the infinite sine product. But before we can actually do that, why don't we actually first expand our infinite sum first to get the bigger picture. So let's see, let's write this out in full. So m is equal 1 of the natural log of 1 minus x squared divided by m squared. So let's say that if I expand this out, so what we have is, so ln of 1, then subtract 1 or x squared divided by 1 squared, add this with the natural log of 1 minus x squared divided by 2 squared. Then I add this with the natural log of 1 minus x squared divided by 3 squared. And then we continue on, so on and so forth. So we notice that we have an addition of natural log. So we actually applied that natural log property. So what we have is, it's going to yield us, we have a natural log, and then everything is into the input in multiplication. So that means I can actually write this in terms of a product series. So this is going to be the natural log of the product series from m is equal 1 to infinity of 1 subtract x squared and then divided by m squared. And of course, as mentioned from Euler's infinite sign product, so what we have is that sine of x is going to equal to x multiplied by the product series. And I also did a whole derivation of this, so if you want to check it out, the link's in the description below if you want to see the whole thing. So m is equal 1, and then now this is going to be, so 1 then subtract x squared and then divided by pi squared and then m squared. And close that off. So what we do is, now let's actually suppose that I substitute x for everything for x times pi, or pi times x. So that means sine of pi x is going to equal to pi x, and then our infinite sum or infinite product, m is equal 1, of 1, and then subtract, so pi squared and then x squared divided by pi squared and then m squared. Okay. And then let's say I divide the pi squared to both sides, so that means sine of pi times x divided by pi times x. And so of course, then those pi squares are going to cancel each other out, so I have the infinite sum or infinite product. I keep getting that mixed up. And then it's of 1, and then subtract x squared, then divided by m squared. Okay, so with this in mind, that means I can actually just substitute the sine pi of x divided by pi x in substitution of our infinite product over here. So now this actually just yields us over here to just the natural log of sine of pi x and then divided by pi x. All right, and so now we actually just go back to over here into that substitution. So that means now I'm just gonna, let's go to a different marker for this one. All right, so now continuing forward, so back to over here. So that means now I'm gonna have is, so negative 1/2, and then the natural log of sine of pi x, then divided by pi x. Then I have a negative, so I can actually put that in front of our, or inside back to our input, so that's the exponent. So what that does is we actually just flip the reciprocal. So now that just yields us with 1/2, and then multiply by the natural log of pi x and then divided by sine of pi x. All right, so again, if not really again, but if you can leave the answer like that if you want to, but we can actually still simplify this further. Otherwise, I wouldn't have mentioned Euler's reflection formula to begin with. And so with that, that's when we'll be utilizing that formula. So we know that the Euler's reflection formula says for pi or gamma of x multiply a gamma of 1 minus x is going to equal to pi and then divided by sine of pi x. Okay, so let's suppose I multiply x to both sides of the equation. So I have an x times gamma x, which that's actually written as the same thing as gamma of 1 plus x. So I can actually just put that, replace that back here. So I have gamma of 1 plus x, then multiply gamma of 1 minus x. And so now that actually just yields us with pi x and then divided by sine of pi x. Okay, and that's just perfect. Pretty much we're done here. We just substitute back our pi x divided by sine of pi x formula, replace this back with the gamma function, and so therefore our sum therefore yields the following answer over here is going to be equal to 1/2 multiplied by the natural log of gamma of 1 plus x and then multiply with gamma of 1 subtract x, for of course the absolute value of x is strictly less than 1 to fit that condition for the convergence. And so with that, that's our nice closed formula over here. That actually concludes our nice little identity relating with the Riemann-Zeta functions of the even indices. So there we have it, just like that. And yeah, that's pretty cool if you ask me.